We were just talking about linear regression, and so this was our setup. So we had linear regression, and we had this setup. We're given some data, some x's and y's. It's a supervised learning problem, and we want to choose some function to predict for new x's, predict the value of y. And we were talking about these basis functions, this beautiful little trick to transform your original x's using some function phi, which is takes you from your original d-dimensional space to some other, say, m-dimensional space. And these things could be nonlinear. And these basis functions can allow you to capture nonlinear characteristics in x, but it's linear. So the key fact is that it's linear. Your function that you're using here to predict this f is still linear in w, in this parameter w. So that was the key fact, linear in w, not necessarily in x. So you can think about this, a way to think about this is that you're just taking, so we've got our original d-dimensional space here, this is Rd, and we've got x living here, and we map x to some other space, Rm. So this goes to phi of x, and our map is phi. And this sometimes people call the feature space. This is our original space, and this is our feature space. And so what the linear thing that we're going to fit is going to be linear in the feature space, but it could be highly nonlinear. So this is just sort of a notional, and this is m-dimensional space, but I'm drawing it in 2 dimensions. And similarly here, but just notionally, you're thinking that this is getting transformed, and over here, this thing which was linear comes back to something which is some nonlinear whatever thing. And so what you can think about this as doing is that, switch back to green, that we had our original x and we took phi of x. So let's call that z. So z is this thing over here, and then our function, it was this dot product with w. So f of x, I haven't really talked about where this comes from, but we'll get to that a little bit later. And if we just plug this in, it's just, of course, the dot product with z. So you can think about, so basically, solving the problem in the case of just the case of when we're dealing with the identity function, right? This is the same as this, except we've replaced x with z. So solving the linear regression problem, which essentially we're going to see boils down to estimating a value of w, we can always reduce it to this case where phi is the identity function by just mapping our original data. If we chose some nonlinear mapping phi, then we would just do that mapping first and then solve it in the new feature space. So from here on, when we're working with linear regression, at least abstractly, I'm just going to assume that we've already transformed our data into the feature space, and that we don't need to think about taking phi again. We're just going to can't consider this simple case here. Okay, so now that we've got that out of the way, let's talk about. So I want to give you an idea for why linear regression is such a natural model in some sense. It's sort of, in some sense, the most natural model for regression. And I'd like to motivate why that is the case. So we're doing a regression, and remember that we could make 2 choices. So we're going to make a series of choices here, which will lead us to to the classic linear regression. So the first choice we could make would be choose a discriminative versus a generative model. So let's say, since in some sense discriminative is simpler, we're modeling less things, we're making fewer assumptions, let's choose a discriminative approach. So this is, so we're sort of, this is sort of a new topic. So we're going to choose a discriminative approach. And what's discriminative? Well, that just means we're just going to model the conditional probabilities on the y's given the x's, right? We're not going to model the whole joint distribution. So let's assume some family, some set of conditional distributions, and let's parameterize them by theta. So this is, as theta varies over some set capital theta, and maybe these are, for example, like vectors in Rk or something like that, for example. So we have some family, some set of conditional distributions like this, and we're going to estimate theta using our data. So we're given our data. Remember, back up here, back to the setup, right? We're given this data, all these pairs of x's and y's, and we're going to use that data somehow, in some way. So, we're going to assume that the data comes from this probabilistic model, or rather one of these, for some. So we'll assume that there is some theta for which our data comes from one of these distributions, and then we'll try to figure out what theta it actually came from. So that's what I mean by this: estimate theta using D. Okay, so that's good. And so, for example, you could use like MLE. The MLE, the maximum likelihood estimate, would be a classic way that you might do this. Okay, so that's good. Now, but what family of distributions should we choose? Well, to make our lives easy, oftentimes the most natural, or the easiest distribution, remember these y's are real valued. This is regression, so the y's are real valued. And for real valued things, very often the Gaussian distribution is the model of choice. Easy and powerful. So let's assume, choose a Gaussian. So in other words, these, let me write it, p sub theta of y given x's will be normal. So I'm going to use a little bit new notation here. I don't think I've used this before. It will be to be the normal PDFs. With theta would be a normal PDF with, say, mean mu and variance sigma squared. Mu of x and sigma squared of x, these are functions of this point x. So x, remember, is in Rd. And here, so where's theta over here? So theta is going to be the pair of functions, mu and sigma squared. So these are functions now. Functions on Rd. Mu is a real valued function. This is a positive function. So this, I sort of said what it is, but just to be a little more explicit, this is just a sort of a shorthand notation that it's very convenient, rather than saying, like, introducing some letter like f. We could say this equals f of y, where f is the PDF for, like I could say this equals f mu of x sigma squared of x of y, where this thing f mu sigma squared is the PDF of normal with mean mu and variance sigma squared. But this is just a much more succinct way to say the same thing. So we could choose these to be these PDFs and for some functions mu and sigma squared. So that's all well and good, but what functions mu and sigma squared should we use? Well, that's where we come to the definition. We'll choose some mu and sigma squared, some functions here, and we will define Gaussian. I'll put this qualifier to emphasize that we're using a Gaussian distribution. Gaussian linear regression. Gaussian linear regression models, it's a probabilistic model for our data, and it models the data D by assuming that we have this conditional, by assuming these conditional distributions take the form normal, just like this, but now we're going to choose some, whoops, not mu, y. We're going to choose some functions here, some mu of x and sigma squared of x. So far I haven't said anything new, and here's where it comes. Here's the linear part. We're going to choose the mean, this mu of x, to be the dot product of w with x. And we will take sigma squared to be a constant, just, this function here, it was a function, but we'll just take it to just be some constant positive number. Where theta, so I put theta here, and where's theta on this side? Well, theta is just, in this case, we can just write it as this, I put mu here, but I'll just, make a new theta, and it'll have this vector w, and this number sigma squared, and, w here is a point in RD, because it's the inner product with that, and sigma squared is just some positive number. Okay, that's it. So that's linear or Gaussian linear regression. And just to emphasize, from this motivation, mu of x here, well, it's just this. It's this dot product. And right, and I already said sigma squared, the function here would just be this constant number. So that is linear regression, or at least Gaussian linear regression, which is the most commonly used form. And another way that you can say the same thing, so we could have also said this in the following way. We could say that we choose this model, we model the y, this is the target variable for a given x, as a random variable, so I put capital Y, and it's a random variable equal to the dot product of w with x, so y is it's the y for that x, plus a random variable epsilon, where epsilon is normally distributed with mean mu and variance sigma squared. So this is the random part here. It's just, you might call this the noise, additive Gaussian noise, people sometimes say. And so this is Gaussian linear regression, and you could generalize this to have more general forms of linear regression, where you replace the Gaussian, instead of using a Gaussian distribution here, you could use some other PDF, some other distribution. But the key fact is that the dependence on x, the point x, is linear in this w. So you always have this linear function of x. So for example, you could have like a Laplace distribution, which is similar. Well, it's quite different, but you could have a Laplace distribution or some other distribution where it's just linear dependence.